Bismillahirrahmanirrahim. Assalamu alaikum. This is Muzammil Ijaz. In the last lecture, we have covered introduction of the basic mechanical engineering and as well as thermodynamics. And we stopped at the properties of thermodynamics, especially pressure. So today we will start from the same point. Before starting, I would like to motivate you people towards this subject, basic mechanical engineering. In the particular practical field, you do not have only theoretical knowledge, your skills, but as well as information and knowledge, which by which you lead people, especially in the execution field. You have a lot of labor inside your team, so you have to lead them. And I would also like to share some of my stories in my industrial experience, that in English Mr. Private Limited, in the seminar, the managing director of the company told us and shared the story of NASA, that people at the NASA, especially sweeper, do their work with their hearts. And they why they are doing their work with the hearts, because they have a very high self-esteem. They think that they do for those people who go to the moon. In the same way, the managing director increase our self-esteem, that they are producing biscuit which people eat in the meanwhile, between the breakfast and lunch. So we have to be the best in the world, the best manufacturer and the largest manufacturer. So that's why people have high self-esteem and motivation, and they produce skills, excellence. In the same way, when you are graduate from this university, you have to make you have to have very strong self-esteem and produce excellence and value addition to the society. Anyway, move towards the topic which we left in the last lecture. Pressure definition, we already covered its definition and its units. In the last lecture, we have seen that pressure in the liquids increase with the depth, because the weight and the weight due to the gravity exert pressure on different level. Like in the top we have a low pressure, but in the bottom we have the highest pressure. So this is the experiment. In the same way, pressure exerts in the atmospheric pressure. When we move above the sea level, the pressure is decreasing. It is well defined by in this
exerts pressure in all directions. For example, here we have the water in a beaker. Due to gravity, this water is pulled down towards the earth. If we divide this water into different layers, then each layer is being pulled down by the earth. Due to this pull, water exerts downward pressure, and this pressure is uneven throughout. That is, the bottom layer experiences more pressure than the top layer. This is because the weight of water above the bottom layer is more, and the pressure decreases as we go upwards. In fact, we saw that the water exerts pressure in all directions and not only in the downward direction. One more thing that we studied about the liquid pressure is that at any point in a liquid, the pressure is the same in all directions. That is, if I take any point here in this water, the pressure exerted by water here is the same in all the directions. Air also behaves in the same way. Just like water, air is also being pulled down by the Earth's gravitational force. This force applies pressure on the air in the downward direction. The pressure exerted by air is called air pressure or atmospheric pressure. Did you know that the atmosphere is divided into different layers? The atmosphere is divided into 5 layers, namely the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The pressure in the troposphere, which is the bottommost layer, is higher than the pressure in the layers above it. And I'm sure you can guess the reason why. This is because the weight of the air above the troposphere is greater than the weight of the air above, say, the stratosphere. The air pressure also acts in every direction and not only in the downward direction. And finally, just like the pressure in liquids, the air pressure at a particular height above the Earth's surface is same in all directions. That is, if I take these 2 points at the same distance above the Earth's surface, then the air at this point will exert an equal pressure in all the directions, just like the air at this point. Let's look at an interesting graph now. A graph which represents pressure at a particular altitude. The graph also represents how the pressure varies from layer to layer. The troposphere layer is closest to the surface of the Earth, and the pressure in this layer goes up to 100,000 Pascal, where Pascals, represented by Pa, is the SI unit of pressure. This is massive pressure. This pressure pushes and pulls the object on the surface on the Earth.
So I hope you well understand by the pressure, atmospheric pressure that exerts in every direction but varies with the height. Like if you fly in the plane above 30,000 feet, the pressure is lower than the sea level. You can see that pressure is like 0.8, 0.7 atmosphere. Anyway, this is general definition of atmospheric pressure of a local atmosphere is known as atmospheric pressure. At sea level it's 1 atm, and we have different units of atm, that like for Newton per meter square, yeah, Pascal is like 101,325 10 to the power 5, and for the psi it is 14.69 pound per inch square. Anyway, as you understand the atmospheric pressure, but the pressure which is above than atmospheric pressure and exerts in our daily life, it's gauge pressure. For an example of a tire, you see that tire elevate the whole car, and it is a higher pressure than air. If we move the plug of the tire, the pressure inside the tire goes out, because pressure goes toward high pressure to low pressure. Around the surrounding of the tire it is atmospheric pressure, but inside it is higher pressure, that is called gauge pressure. In the same way, oppositely, if you have a cylinder and it is a positive pressure, if we have a cylinder but it is have a gauge pressure higher pressure than atmospheric, air is getting out from this cylinder to the atmospheric pressure. But if we remove the air and make the vacuum and stop the lid, when the lid open, the opposite happens. Atmospheric pressure goes into the air from atmospheric pressure goes into the cylinder due to the vacuum. So we have another definition that is called vacuum pressure. The pressure which is greater than atmospheric pressure, it is called gauge pressure, and the pressure which is less than atmospheric pressure is vacuum pressure. And it is well defined by this equation, and the pressure which accumulates both pressure, it's called absolute pressure. This is C, no, this is not C, this is absolute pressure. So absolute pressure is sum of atmospheric pressure and the gauge pressure. But if the external pressure is negative, it's called vacuum, and in this case the absolute pressure is equal to atmospheric pressure minus vacuum pressure. By that definition, you can see that pressure below atmospheric pressure are called vacuum pressure, measured by the vacuum gauges. The actual pressure is given in at a position is called absolute pressure, and it is measured relative to the absolute pressure. This pressure related to each other by this formulation. This picture well represent the absolute pressure, the gauge pressure, and the vacuum pressure. So in the first case, you see that the absolute pressure is sum of gauge pressure and atmospheric pressure, and in the vacuum case it is opposite. So absolute pressure is atmospheric pressure minus vacuum pressure. So in the positive pressure, it is sum of gauge pressure and the absolute pressure, but in the condition of vacuum, it is atmospheric pressure minus vacuum pressure. Anyway, As you seen that variation in depth or height change the external pressure or gauge pressure. For that particular example, pressure does change in the horizontal direction, doesn't change in the horizontal direction. As you see that the pressure at this point or this point is the same, but as we move on, the pressure will increase due to the weight of the water and also the atmospheric pressure of air. But pressure in the fluid increases with the depth because more fluid rests on the deeper layer, change in the pressure, and it is defined by the formula P is equal to rho GH. Sometime it written like this and sometime it written like this. Both parameter are used for the density of the fluid. So the formula is density time gravitational acceleration multiplied by height, and the unit is same, Newton per meter square, as written here. So in the same way, if we calculate the total pressure at point 2, it is sum of at atmospheric pressure plus gauge pressure, and the gauge external pressure is due to the weight of the liquid. So we open the formula QGH or rho GH. Now move towards one numerical in which we have determined the pressure exerted on a diver at 30 meter below the free surface of the sea. Assume atmospheric pressure of 101 kilopascal. The sea level is 101 kilopascal, means 101,325 pascal. Kilopascal is 10 ki power 3, and the specific gravity of C is 1.03. In the last lecture we studied specific gravity. The simple formula of specific gravity is the density of any fluid, like in this case the density of seawater divided by the density of standard water. So first of all we have to find out the density of seawater, because in the formula as you seen that if you need to calculate the pressure at 30 meter depth, like in this case the depth is like 30 meter. So we know the height, we know the gravitational acceleration, that is 9.8, but we want to calculate the density. So for the density we first apply the formula of specific gravity, as E is equal to density of seawater and the density of water standard, that is 1000. So Sg is 1.03, and the density we need to calculate of seawater in the short form we write as W, and the density of standard water is simple 1000. So density of seawater is 1030. Now in second stage we apply the formula absolute pressure. P absolute is equal to P atmospheric plus P gauge, and P gauge is simple rho GH. In the numerical we already tell us the atmospheric pressure, that is 101 kilopascal. So we have to set one unit, whether you can set the pressure or kilopascal. If you set atmospheric pressure in kilopascal, you also have to calculate the gauge pressure in pascal. This formula in SI unit gives the pressure in the pascal. So we have to divide the whole rho GH by 1000 to make kilopascal. So now we have a density 1030 multiplied by gravitational acceleration 9.8 multiplied by, this is 9.8 multiplied by height, that is 30 meter, and the whole equation divided by 1000 to make it kilopascal. So now 101 kilopascal plus, if you calculate this, it gives the value of 303. So P absolute at point 2 is now becomes 404 kilopascal. So in this way we have calculated the atmosphere the total pressure at 30 meter depth below from the sea surface. This is the answer. This numerical taken from the book Sengel, Thermodynamics and Engineering Approach by the author of Sengel, example 1.55. So I hope you well understand the idea. We have done numerical as well with definition, which gives the idea in the deviation of the depth. Now move towards the next slide. Now we have to study some of the basic tools which calculate the pressure. The most basic and the most significant tools which calculate the gauge pressure is Borden gauge. You see that this type of analog parameter in different machines, like if you go to the shop of uh, tire shop, you see that the cylinder in which air which is compresses in the cylinder shows the pressure by this Borden gauge. In many other in your laboratories, you see that parameter which showing the pressure of the liquids or in the fluids or the gases. So the main principle of working this Borden gauge is simple. It is a copper tube in which the air or any fluid enters with the pressure, and due to the pressure it is spiral shape. So when the pressure exert on this spiral shape, it tends to move in this direction, and when it tends to expand, and when it is expanding, it's moved towards upside, and it is knocked by this lever and gear mechanism. When it moves towards here, it moves this gear, and due to the gear, the needle moves left to right, which shows the variation of the pressure. So it calculate the different it calculate different so it calculate different gauge pressure, that is external pressure, and the same Borden gauge can also be used to calculate the vacuum pressure. So when it is fit in any vessel which have a vacuum pressure, it tends to compress, and due to the compression it moves towards this direction, and which rotates the gear lever mechanism, which move the needles and push toward the left side. So the Borden gauge is used to calculate gauge pressure as well as vacuum pressure. Now move towards the next tool which calculate the atmospheric pressure. This is simple a barometer which calculates atmospheric pressure. In the diagram, you can see that in the vessel it is filled with the water, and simple tube is also filled with the water. So when the air pressure is higher, it exerts pressure, and it tends to pull water above, and this height shows the give the variation of the pressure. Like if we place this setup at some building height like 30-meter or 40-meter height building, the pressure of air becomes lower, so water get out from the tube and show the lower level. But if we move towards the sea level, it levels becomes higher. So this shows the different level of water, which represent the different atmospheric pressure. Like height of the column is air pressure, and not only liquid, that is a tube and liquid pressure calculates. We also have gauges like Borden gauge which calculate the atmospheric pressure, but in that case it is also called barometer. Like in planes you have a board, you have a you are calculating the atmospheric pressure not by this vacuum and level parameter, because it is very sensitive and water can move out in the vibration. So we have to have a parameter like this Borden gauge, and but in that case Borden gauge is not called Borden gauge, is also called barometer. Now we have another pressure measuring tool that is called manometer. It is also used to calculate the external pressure, whether it is a vacuum or gauge, by simple level of the water. Like in this case you can see that in the figure, if in this case the tank is filled with the positive pressure, so it is exerting pressure on the fluid, and due to the fluid it moves the level. So on the both level of the U-shaped tube, the level of the liquid is different. Here it is this, and it is this. If we open the vent and remove all the external pressure to the atmospheric pressure, it level becomes same like this. So on the same pressure it is level becomes same. So the variation of this level or the difference of this liquid level tube shows the external pressure. We have a very good animation of this.
Initially, the U-tube is filled with a manometric fluid such that the level of the fluid is same in both the limbs. The manometric fluid in the U-tube can be oil, water or mercury whose density should be known. There are two limbs in the manometer, L1 and L2. A graduated scale is fixed between the two limbs. When both the limbs are exposed to same pressure medium, the fluid level in the two limbs will be equal. Now let us measure the pressure of air trapped inside the tube. The limb L1 is open to atmospheric pressure and the limb L2 is connected with the rubber tube. The rubber tube consists of a clip to make it airtight after the air is blown through it. The pressure of the air in L2 is now greater than the pressure in L1. Now the fluid in the U-tube is displaced to a new position. The difference between the two readings will give height of the fluid level in the tube. The formula for calculating the pressure of air trapped inside the tube is given by P equals rho dH. On substituting the corresponding values in the above formula, we get the pressure value. Let us now measure the pressure of the water column. The limb L2 is connected with the rubber tube. The end of the tube consists of a funnel closed with a rubber sheet. This tube is then inserted into a beaker of water whose pressure is to be determined. The rubber tube with the funnel is pressed down so that the pressure is induced through the rubber sheet to the tube. Now the manometric level in L1 rises and simultaneously the level in L2 falls down. The difference between the readings on the graduated scale is the height h. The pressure of a water column can be calculated as done before. Thus you have learnt about the pressure measurement using U-tube manometer. In this media, you will learn about the use of manometer in turbocharger filter. U-tube manometer is used mainly to measure differences of pressures. The manometer is filled with suitable liquid. The two ends can either be connected to two sides of a machinery or one end connected to a machinery and the other end open to the atmosphere. Manometer used for turbocharger filter. In a turbocharger blower filter, one end is connected to the air intake casing and the other end open to the atmosphere. When the turbocharger is not running, the liquid level is same in both the limbs. Manometer will show the pressure drop in the blower filter. Moreover, it can be used for monitoring the cleanliness of the filter. Please note that as a filter gets dirty, the level difference in the manometer increases. Thus, you have learnt about the use of U-tube manometer in turbocharger filter.
So to I hope you well understand by the idea of manometer and how it is calculating the difference of the pressure, whether the difference in the machine or whether calculate the vacuum pressure in the simple, in this example, turbocharger, the cleanliness. When this filter is choked, when the air is moving out from to the machine and the filter is choked, it producing vacuum, and due to the vacuum it's showing the difference reading of the height, which tell us the cleanliness factor. Like when the vacuum pressure is exceeding that its defined point, we need to clean that filter. So you can also take example for your civil infrastructure. We have one kind of numerical in this Sangel book, in which we are calculating the height of the building with the help of barometer. Like in the ground level, we know the atmospheric pressure is 1 atm, and at the height like 60 meter or 70 meter, the atmospheric pressure is calculating by the agency, and we have a chart of atmospheric pressure at different height, that is called ASI, air standard pressure. We have I will show in the later slides the ASI chart, which showing the different atmospheric pressure at different height. So if we know that atmospheric pressure at ground level, that is 1 atm, and let's suppose in the level of at the 60 meter height of the building, we have atmospheric pressure like 0.8 atm. So we know the difference of atmospheric pressure. If we apply the formula P is equal to rho gh, we know the density of air, we know the gravity, we can easily calculate the height. Like from PATM, we know the atmospheric pressure like 60 meter, density of air we know, we can take from the books, we know the gravity, and then we calculate the height of the building. So we have a different application of the pressure. You can take it for your civil application. Later we will also do some of numericals related to the civil engineering. But now we have numerical example 1.6 from the same book, Sangel. A manometer is used to measure the pressure in the tank. As you see in the video, the fluid used has a specific gravity of 0.85, and the manometer column height is 55 centimeter, shown in the figure. If the local atmospheric pressure is 96 kilopascal, determine the absolute pressure within the tank. So we need to calculate the gauge pressure first, and then we calculate the absolute pressure. So we apply the same formula, P absolute is equal to P atmospheric plus rho gh, that is gauge pressure. Now P absolute is equal to atmospheric pressure is 96 kilopascal. So we also set this rho g8 in the kilopascal factor, so we divide the whole formula by 1000. We can set this 1000. Density of this fluid is 0.85. Specific gravity is 0.85, so we calculate the density, and by a simple formula now I will write directly that density of the specific fluid is equal to specific gravity multiplied by density of water, that is 1000. So 0.85 multiplied by 1000 is 85. So it's 850. So we directly write 850 multiply by 9.8, and height 55 centimeter we have to write in the meter. So by converting 55 centimeter into meter, we have to divide 55 divided by 100, so it's 0.55. So multiply and divide by this all factor, we can calculate 850 multiply by 9.8 multiply by 0.55, it is 4581, and when we divide 4581 divided by 1000, it is 4.58. So 96 kilopascal plus 4.58. Oh no, it's another. So we have the answer 100.58. You can convert 100.58 to 100.6 kilopascal. So this is the answer. Now you have video of manometer and as well as the example of manometer. So in this way we calculating the gauge pressure, the atmospheric pressure, and absolute pressure. If we place this device out and put the gauge pressure, and we in that way we have to find that gauge pressure will be showing directly the vacuum pressure, and when we add this atmospheric pressure we get absolute pressure. Like in the other example, like example 1.37, the figure shows tank. Now we will continue in the next lecture with this numerical, inshallah.